Ordinary crystals are defined by a pattern that repeats in space. Atoms arrange themselves in a regular lattice, sodium, chlorine, and that structure extends outward in every direction. The pattern is spatial. Time crystals are stranger. They repeat in time. Instead of a lattice frozen in 3 dimensions, you have a quantum system that cycles through configurations, state A, state B, state A, state B, in a persistent rhythm that does not decay and does not require external energy input to sustain itself. That is not supposed to happen. It breaks time translation symmetry, meaning the system does not look the same at every moment. It has a built-in clock ticking from within. And that raises a direct question. If time crystals naturally generate periodic signals, can they be used as actual clocks? And if so, are they any good at it? A team led by physicist Ludmila Viotti at the Abdus Salam International Center for Theoretical Physics in Italy set out to answer that question in a paper published in Physical Review Letters in early 2026. The result is not that time crystals will replace atomic clocks tomorrow. The result is that time crystal in order, in principle, mathematically, may provide a real advantage in quantum timekeeping, and that makes time crystals worth investigating beyond their status as a theoretical curiosity. The study is built on a controlled comparison. The researchers simulated a system of 100 quantum particles, each with a property called spin. Spin is a fundamental quantum attribute, and in this model, each particle can exist in one of 2 states, spin up or spin down. Together, these 100 spins create an enormous number of possible collective configurations, and the system evolves over time according to quantum mechanical rules. What makes the setup useful is that the same system can exist in 2 distinct phases. In one phase, it behaves conventionally. In the other, it enters a time crystalline phase where a repeating pattern emerges spontaneously. That allows for an apples-to-apples test. Same particles, same interactions, different phase. Does the clock perform better when time crystalline order is present? To evaluate that, Viotti's team calculated 2 specific measures of performance: accuracy and precision. Accuracy refers to how close the clock stays to the correct time. Precision refers to how consistently the clock can resolve small time intervals. Both matter. A clock that drifts too far from the correct answer is useless even if it ticks very precisely. A clock that cannot distinguish fine intervals limits the measurements you can make. Ideally, you want both. In the conventional phase, the clock runs into a familiar problem from quantum metrology. When you try to increase resolution, meaning you want to distinguish finer slices of time, accuracy rapidly degrades. This trade-off is not unique to time crystals. It is a general feature of quantum systems, where extracting more detailed information often comes at the cost of reliability. More precision, worse accuracy. That is the limit. In the time crystal phase, however, the behavior is different. The oscillations associated with the time crystal in order provide a more structured and stable timing signal. The calculations suggest that the clock can maintain significantly better accuracy at the same resolution compared with the non-time crystalline phase. The improvement is not infinite, there are still limits, but it is measurable, and it comes from the phase itself. The periodicity is not imposed externally, it emerges from the collective behavior of the spins. That is what makes it scientifically interesting. The clock is being driven by the quantum phase of matter itself, rather than by an external laser or microwave field. None of this has been built in a laboratory yet. The results are mathematical. Viotti and her colleagues performed detailed calculations based on known quantum mechanical equations, but no physical device currently exists that operates as a time crystal clock. That gap between theory and experiment is not a failure of the work. It is the nature of theoretical physics. You calculate what should happen under ideal conditions, then experimentalists figure out how to make it real. The question now is whether real quantum systems, trapped ions, superconducting circuits, cold atoms, can be configured to reproduce this behavior under realistic conditions. To understand why the result matters, it helps to know what time crystals represent in modern physics. The concept was first proposed by Frank Wilczek, a Nobel laureate, who asked whether a system could break time translation symmetry in the same way ordinary crystals break spatial translation symmetry. For years, it was an open theoretical question. Then, in 2016, the first experimental demonstrations appeared. Researchers working with trapped ions and other quantum platforms successfully created states that exhibited persistent, repeating oscillations in time without continuous external driving. Time crystals were real. Since then, the field has been asking a follow-up question. What are they good for? Time crystals are fascinating as a new phase of matter, but physics is littered with exotic phenomena that remain confined to specialized laboratories. If time crystals are going to matter beyond academic interest, they need to do something useful. Viotti's work provides a concrete answer. They might make better clocks. Clocks are important, not in the everyday sense of knowing when your meeting starts, but in the technical sense of synchronizing systems. navigating precisely, testing fundamental physics, and probing the environment. Modern GPS systems, for instance, rely on satellite-based atomic clocks to provide accurate timing signals. Those signals can be disrupted, spoofed, or jammed. Alternative clock platforms that operate independently could become valuable in secure or specialized contexts. Time crystal clocks would not replace GPS, but they might provide resilience where current systems are vulnerable. Another application is sensing. A clock based on time crystal oscillations would likely be extremely sensitive to disturbances. Even weak magnetic fields or small environmental changes could shift the timing signal. That means time crystal clocks could double as precision sensors, similar to how atomic clocks are already used to detect gravitational waves, measure Earth's magnetic field, and test theories of relativity. If you can measure time very precisely, you can measure anything that affects time. That turns clocks into universal measurement tools. The challenge, however, is engineering. Time crystals are delicate quantum states. Building a device that stabilizes them, reads them out reliably, and operates outside of specialized laboratory conditions is far from straightforward. Scalability, noise resistance, and practical readout mechanisms are all open problems. The fact that something works in a calculation does not mean it works on a benchtop. Experimentalists will need to find platforms where time crystalline phases can be controlled and maintained, and where the timing signal can be extracted cleanly enough to compete with existing clock technologies. Still, the progress is real. Time crystals have moved from speculation to demonstration. Multiple research groups have created time crystalline phases in trapped ions, superconducting qubits, and condensed matter systems. The field is no longer asking, can they exist? It is asking, what can they do? Viotti's work contributes to that shift by providing a quantitative benchmark. It shows that time crystals are not just interesting phases of matter. They are phases that could, in principle, outperform conventional designs in specific timekeeping tasks. Expert commentary supports this view. Mark Mitchison at King's College London, who was not involved in the study, noted that almost any system can function as a clock if you track events carefully enough. But a system with self-sustained periodic behavior is naturally closer to what a clock needs from the start. That reduces the burden of extracting timing information from randomness or noise. Time crystals fit that description. Their periodicity is intrinsic. It does not fade. It does not need continuous input. It is the phase. Whether that advantage translates into practical devices depends on what happens next. The calculations are done. The path forward requires experimental verification, platform development, and engineering innovation. If those steps succeed, time crystals may eventually serve as building blocks for quantum-enhanced measurement tools, not necessarily replacing today's best clocks, but expanding the range of what quantum systems can do. From theoretical curiosity to potential technology, that is the trajectory.